AP Chemistry students, this is your lesson 8.2 about pH and pOH of strong acids and bases. We are working towards an enduring understanding that the chemistry of acids and bases involves reversible proton transfer reactions with equilibrium concentrations being related to the strength of the acids and bases involved. In this lesson, we will learn to calculate the pH and pOH based on the concentrations of all species in a solution of a strong acid or a strong base. So recall that the strong acids and strong bases are these 6 each. So our strong acids include the chlorine, bromine, and iodine from our halogens group, plus perchloric, nitric, and sulfuric. And then on our strong bases side, we have lithium, sodium, potassium from our group 1 alkali metals, and then calcium, strontium, and barium hydroxide from our group 2 alkaline earth metals. Also from your green sheets, we have the relationships for pH, pOH, KW, pKW, and then this is a little note for us. A change of 1 pH unit represents a 10-fold increase or decrease in ion concentration. So this is going to lead to a little shortcut for us about how to calculate pH a little bit later. So for strong acids are strong electrolytes. So electrolytes are just ions that dissociate in aqueous solution. And when they do this, ions, because they're charged particles, can conduct electricity because they're moving charges. And so for monoprotic strong acids, mono means one, protic for the proton. So a monoprotic strong acid will donate 1 hydrogen ion for each dissociation reaction. So for monoprotic strong acids, the concentration of the acid is equal to the concentration or molarity of the hydronium ions. So concentration of the acid equals the concentration of the hydronium ions. For H2SO4 only, the first hydrogen dissociates completely according to the reaction H2SO4 plus water yields HSO4 negative plus hydronium. However, in a reaction with a base, both hydrogen ions will react. So here's our first quick check. What is the pH of 0.01 molar solution of hydrochloric acid? So hydrochloric acid is monoprotic, has 1 hydrogen ion. Each time it dissociates, produces 1 hydrogen ion. So that means that the concentration of the acid will be equal to the concentration of the hydrogen ions. So when we calculate pH, pH is equal to the negative log of that concentration, 0.010. And so when we calculate this, we saw a minute ago there was that hint about how a change of 1 unit on the pH scale corresponds to a power of 10. So in this case, we can count powers of 10 as a shortcut to calculate the pH. So I have my 1 is in the second position after the decimal, and so my pH is going to be 2. In the next example, the pH of 0.00001 molar solution of HI, which is, again, monoprotic. So when I calculate this, the concentration of the hydrogen ion will be equal to the concentration of the acid solution. So pH is equal to the negative log of 0.00001. And so again, I can count those decimal places, 1, 2, 3, 4, 5. And so the pH is going to be equal to 5. For the last example here, my H2SO4, it said would dissociate completely for the first hydrogen ion. And so when I calculate this, H2SO4, I'll take the pH is equal to negative log of 0.1. And so the negative log of 0.1, my 1 is in the first place after the decimal, and so that'll be equal to 1. Strong bases are the soluble hydroxides, and those are our alkali metal bases and our alkaline earth metal, group 1 and group 2, are the strong bases. And so these dissociate completely in water as well, and therefore are, again, strong electrolytes, meaning they will conduct electricity. For our strong bases, we can calculate the concentration of the hydroxide ion using the initial concentration, or molarity, and the ratio of the hydroxide ions in the formula. So the concentration of the hydroxide ion will be equal to the concentration of the base. So here's our quick check. What is the pOH? Remembering that P just means we take the negative log of the thing that it's next to. So I'm taking pOH is equal to the negative log of the hydroxide ion concentration. And in this case, I have NaOH, and so I produce one hydroxide ion for every time it dissociates. And so this will be equal to the negative log of 0.0001. And using my shortcut, I count 1, 2, 3, 4 places, and so the pOH will be equal to 4. Next example, what is the pOH of a 0.01 molar solution of potassium hydroxide? So I produce one hydroxide ion each time it dissociates. So the pOH is going to be equal to the negative log of the concentration of the hydroxide ion, which is, in this case, equal to 0.01. And my 1 is 2 places after the decimal. So the pH is 2. Or I'm sorry, pOH is 2. Last example here. They want me to take the pOH of a 0.1 molar solution of calcium hydroxide. And you'll notice calcium hydroxide produces 2 ions of hydroxide each time it dissociates. So the pOH is equal to the negative log of, now I have to double this, 0.2. And so the negative log of 0.2 is 0.7. So the more concentrated an acid is, the lower the pH will be. So here's my pH scale here on the bottom. And so 0 is on the more acidic end, 7 is neutral, and then more basic, the scale goes up to 14. And again, this is at 25 degrees Celsius because we are talking about, this is based on K values. Okay, and the K values change when the temperature changes. So my pOH is about a measure of how basic something is. And so the pOH is the reverse scale. And so 0, the most basic, is over on the right there, and the least basic is 14, again 7 being neutral. So as we get more acidic, we have an increasing hydrogen ion concentration, and as we get more basic, we have an increasing hydroxide ion concentration. In our previous lesson, we saw that temperature affects the K value for water. So when we change the temperature, it has no effect on the stoichiometry, meaning the balanced equation, and the mole ratio. So our calculations for pH and pOH don't change, but the K value will change. And so our total scale will change when the temperature changes. So this example asks what is the pOH of a 0.2 molar hydrochloric solution at 0 degrees Celsius. So pOH is going to be equal to, I have to find the pH first. So pH is equal to the negative log of 0.20 because monoprotic, so I could use the concentration of the solution. And so this will be 0.7. And then I want the pOH, so I'm going to take the pOH is equal to the pKW minus the pH. So pKW is 14.8 minus 0.7. And so the pOH is going to be equal to 14.1. Here's our together problem. We'll find the pH of a mixture of 10 milliliters of 0.001 molar solution of potassium hydroxide and 10 milliliters of distilled water. So we are diluting our solution here. So I need to first calculate the new molarity of my potassium hydroxide. So I have M1V1 is equal to M2V2. So my M2 will be equal to M1V1 over V2. So this is equal to 0.00100, that's my molarity, times the original volume, 10 milliliters, over the new molarity is 10 plus 10 milliliters. So essentially, 10 divided by 20, that's 0.5. So half of this original value. So I'll have 0.00050 is my new molarity. So calculating the pH is equal to the negative log of 0.0005 and the pH here is going to be 3.3. Remember that when you give your answers for pH, if you have one significant digit in your concentration, that means one place after the decimal in your pH. Okay? So this is the we do. The question asks, how would you adjust 100 milliliters of sodium hydroxide solution with a pH of 12 to a pH of 11? So let me analyze the old solution first. So I'm starting with pOH is equal to my pKW, in this case 14, minus my pH to find my new molarity. So this is equal to 14 minus 12, so that's 2. And then the concentration of the hydroxide ion is equal to 10 to the minus pH, or pOH. So that'll be 10 to the negative 2. So my old solution has a molarity of 0.01 molar. My new solution, I wanted to have a pH of 11. So the pOH will be 14 minus the old pH, or the new pH. So that'll be 14 minus 11 is equal to 3. And now finding the new concentration of hydroxide ion that'll be 10 to the minus of the pOH is equal to 10 to the minus 3, or 0.001 molar. So again, I want to use that M1V1 equals M2V2. So M1V1 equals M2V2. So I want to find the new volume, V2. So V2 is going to be equal to M1V1 over M2 is equal to 0.01 times 100 milliliters divided by the new molarity, 0.001. And so this comes out to V2 equals 1,000 milliliters. So I have to add 900 milliliters to my original solution to change the pH from 12 to 11.